All right, let's get to it here, my friends. So in the real world, we're going to talk about different numbers today, types of numbers, which sounds crazy, I know. There's different numbers, of course, to measure and compare different quantities. For example, we measure temperature. I feel like it's science class right now. Length, height, weight, blood pressure, distance, speed, acceleration, energy, force, angles, age, cost, and so on. Or my awesome archery scores. But anyway, numbers also allow to express relationships between different quantities, radius, volume of a ball. Hey, here's a little throwback to geo, radius, volume, love it. Miles driven, gas used, or between education level and starting salary. So looking at different types of numbers. Now, some of them, you probably know what integers are, I'd have to guess. Natural numbers, probably, that might be something new to you. But we also look at all these different sets of numbers. So first off, natural numbers, you can see 1, 2, 3, 4. So notice some things with that. There's all whole numbers. There's no decimals or fractions. 1, 2, 3, 4, so on and so forth. And notice it starts with 1, not 0. Natural numbers start with 1 and go up. Okay, all right. Now, these are all different types of real numbers. Integers, natural numbers with the negatives and 0. Okay, so no decimals still, no fractions. So for instance, obviously I'm going to put some negatives on here. -3, -2, -1. Remember the dots on either side just means they go on forever. So whole numbers, no decimals, fractions, and the negatives, positive, 0. Rational numbers, ratios of integers. Now ratios is one of my favorite words in math because it really means fraction. And I love fractions. You're comparing numbers together. So a rational number really just means you can write as a fraction. So, I mean, I'm just going to give you an easy fraction, a half. We can go all day on fractions, 3/5, 2/3, etc. What about this? 0.17. Can you really write that as a fraction?
Yeah.
That's 17 over 100, 17 hundredths. So obviously we can have some fraction, decimals, etc. What about this one? Let's test your number sense here. That's really 1/3, okay? So anything you can write in fraction form, even though it might be a decimal to kick it off, anything you can write as a fraction really is also a rational number. All right, you probably know this. We, of course, cannot divide by 0. If you try to type 7 divided by 0 in your calculator, it's going to give you a little error, angry message because 0 under the line is undefined. Can't do it. Can't divide by 0. Now, always the why on that. You're like, why do you get this error message? So like I said, if we're going to try to do, let's say, 7 divided by 0, I'm just going to go old school long division. 7 divided by 0. Well, just like when you learned long division back in, I don't know, 4th grade, what times 0 is 7? I can't do it. Anything times 0 is 0. There's no way I can multiply 0 by something to get a 7. That's why, all about the why, you can't divide by 0. All right, also, irrational numbers. Real numbers that cannot be expressed as a, my favorite word, ratio, fraction, of integers. So now you cannot write it in fraction form no matter how much you want to try or do it. So for instance, let's do a square root. So if you type the square root of 2 in your calculator, it's 1.41. All the numbers don't repeat. There's no pattern. It goes on forever. There's no way you can write it in a fraction form. Or, I got to take it back to geometry, because I know you guys loved geometry last year, right? Do you miss proofs? You're going to be sad. There's like no proofs in this class, but anyway. What is pi as a decimal? 3.14, goes on forever, doesn't repeat, there's no pattern, you cannot write it as a fraction. How is pi, throw back to geometry, I can't help myself, how is pi actually calculated?
Just use 3.14.
But why is it 3.14? How are they calculating the 3.14? It's a ratio on a circle. Ian.
The circumference, the diameter.
of the circumference divided by the diameter. If you take any circle, whether it's my small little watch circle, my clock circle, if you measure the circumference and divide it by the diameter, it's 3.14, it's pi. That's how it's calculated. Come on, we should know that from Honors Geo. Okay, last thing I'm gonna throw on this one, you're gonna see real numbers a lot in this class and a lot of symbols, shortcut notation. Who wants to write out the word real all the time? There is a mathematical symbol for it. Here's the symbol. I never write the word real, I use the symbol. So it's kind of like a 2 vertical lines and then the R. So that's the notation for real numbers. You're welcome to use that. Write the word real, doesn't matter to me. Now, everything we've talked about up here is a real number. So you might be like, well, why do I even have to write real numbers if they're all real numbers so far? Valid question. Eventually, sooner rather than later, this might be new to you, we're going to cover or talk about imaginary numbers. Numbers fall into 2 categories, real, up here, and then we're going to get into imaginary numbers. For instance, what's the square root of -4? If you type it in your calculator, what's it going to say? Error. You can't do it because it's the imaginary number 2i. Wait for that in another section. All right, getting carried away, kids, getting carried away. So some properties of numbers. There's nothing for you to write down here. We're just going to look at this. Good to know the words for the properties, but in my eyes, this is really common sense, my friends. Commutative property. The order you add in doesn't matter. 3 plus 7, 7 plus 3, it's 10. Either way you do it. Same for multiplication. 3 times 5, 5 times 3, you get 15. Order doesn't matter. That's the commutative property. Associative, when you're adding 3 different values or multiplying, it doesn't matter if you pick whatever 2 to add first and then do the third. It won't matter. You'll get the same number, same answer. That's your associative. And I know we all know the distributive property. You can only distribute over addition and subtraction. Just a little review on that. Of course, your distributor, most of the times it is in front of the parentheses, but it could be in the back, of course. Doesn't matter. Just make sure you distribute fully through your parentheses. Any questions I can answer for anybody on the first page so far? Too easy. Flip it. You probably don't even need me to do the next one. Love the beginning of the year. Hey, distributive property. Crushing it today. I'm sure we can all distribute. So run our 2 through 2 times x, 2 times 3. Don't make it any more complicated than that. Now, next one, same thing, we're going to distribute. Just a little recap. It's been a while since Algebra 1. You could do your old school FOIL. Remember what FOIL stands for? First, outer, inner, last. If you like FOIL, do FOIL. I don't care. I'm just thinking of this as a double distributive problem. First, you're going to take a through, so a times x, a times y. Then I'm going to take b through, b times x, and b times y. If you want to use FOIL, do it. Like I said, I don't care. My only thing with FOIL that I pro-con with FOIL only works on specific problems. FOIL only works on a binomial, 2 terms, and a binomial, like this problem. But if I had a binomial and a trinomial, I can't FOIL. It's just straight distributing. So that's kind of the one thing I don't love about FOILing. It only works on specific problems. Now, 4 terms, none of them have the same variables, no like terms to combine. That is as good as it's going to get. We can distribute. Like I say, you don't need me to do those. Okay, negatives. Pretty sure you know how positives and negatives work. So of course if you multiply by -1, it changes the sign. 2 negatives make a positive. Same thing, 2 negatives make a positive. Distribute the negative through, it changes the signs on everything. I feel confident you can handle negatives. We don't need any more of a discussion there. Okay, use properties of negatives. Of course, we're just going to distribute through. We're going to be super conscientious of our signs. So negative times x, negative times +2. So it just switches the signs. Too easy. All right, same thing here. Watch your signs. Negative x, negative in the y. And of course, ooh, exciting, 2 negatives make a positive. That's a sloppy plus there. All right, any questions on distributing your negatives? Figured not. Everybody's favorite topic next, fractions. Now, I probably love fractions more than you guys do. It's okay. Let's talk about our calculators. can you use your calculator in here to do the fraction work? I mean, yeah, okay. I'd say, I don't know, 95% quizzes, tests, etc. You can use your calculator on. Once in a blue moon, sometimes, I make you take a no calculator quiz or test, just to make sure we're not totally dependent on our graphing calculators. So it is important we know how to do fractions by hand. Plus, especially if the numbers are small, I can add small fraction numbers together way faster than I could type it in my calculator. That's just me though. So let's just review our fraction operations. Easiest of them all, multiplication. Just multiply across the tops. Do the bottoms, easy. Dividing, multiply by the reciprocal. You have to flip that second fraction. Adding and subtracting, we'll do subtracting too, are the tough ones. You need those common denominators. That's where it gets a little bit of work. Same thing, 4 is just talking about making sure you have that common denominator. 5 is a good one, of course. If you have the same value here, you can cancel those out. You can reduce your fraction down. And of course, the last one, here I look at 6. They're just really showing you or reminding you you're doing cross products really. When you have a proportion, there's a good word for you, 2 ratios, 2 fractions that equal a proportion, you can use your cross products on that. So we're just going to review, because it's not everybody's favorite, we're just going to review some fraction operations for a second. And we're not going to use our calculators. Get scared. So I'm going to make a common denominator. I'm looking at the bottoms, 3 and 5. Small, easy. We're going to turn them into 15ths. I hate the squeak. So of course, to turn the first denominator 3 into a 15, we would times by 5. But you have to do both the top and the bottom by 5 to balance your fraction. 5 times 2. So 10 15ths is the same thing as 2/3. It's just in a different form, different style. We're going to have times this guy by 3 to get it to 15. 4 times 3. Now, of course, you've got that common denominator. You can just add up the numerators, the tops. 10 plus 12, 22 15ths. Last question for you. Can you reduce it? Does anything divide into 22 and 15? So we cannot reduce it. Technical vocabulary. Is that an improper fraction or a mixed number? Improper. Does it say we have to make it mixed number? No, so you can leave it. I don't care. How, just for fun, what would it be as a mixed number? Jocelyn?
1 and 7, 15.
Perfect. And if I don't say, hey, I want it as a mixed number, I want it proper, I don't care. So I'm super specific with directions. It doesn't say, I'm not going to do any extra work. I'm just going to leave it. All right, 6 and 4. What's your common denominator for 6 and 4? 12. So let's turn them into 12s. Now, some of you can probably just do this in your head. To turn 6 into 12, of course, get it times by 2. Do the top and bottom, 2 times 1. To turn 4 into 12, let's multiply by 3. 3 times 3. So 2 12s minus 9 12s. 2 minus 9, negative 7. So just a little basic fraction action just to review. And yes, I know there is more. Get ready for the next one. Those are easy. Okay, we've got a fraction nightmare on C, okay? You're adding fractions in the top, you're subtracting fractions in the bottom, you're dividing fractions, the whole thing. Now, lots of different ways you could approach this problem. Obviously, none of them are wrong. Here's my pro tip. I'm looking at the bottoms, 3, 2, 4, 6. I mean, I could make a common denominator just on the top, just on the bottom, and work on it. But honestly, I think it's small numbers. Easiest, let's just turn them all into the same denominator. All 4 fractions I'm going to make the same denominator on. I think it's going to make our life easy. So I'm like 3, 2, 4, and 6. Let's turn everything into 12s. I'm going to start up here. So of course, 3 goes into 12. We'd have to multiply by 4, 4 times 1. And of course, 1/2 is equivalent to 6 12ths. And we're going to add that up, yes, to 10 12ths in a second. Let's do the bottoms. So to get 4 into 12, we'd have to times by 3. I'm going to do the numerator by 3. 6 to 12, I times by 2. 5 times 2. So let's do the adding and subtracting. Let's combine the top fractions and the 2 bottom ones. So 4 12, 6 12, I got 10 12ths on the top 9 minus 10, we've got negative 1/12 on the bottom. When you divide two fractions, you multiply by the reciprocal. So I'm going to keep that top one, and I'm going to reciprocal, I'm going to flip the bottom one. So I'm going to make it negative 12 over 1. Hey, and this one works out pretty nice because what happens to your 12s? Cancel. Final answer, negative 10. Who needed a calculator for that? We don't. So now, am I going to know if you use your calculator on the homework? I'm not. But we should be trying to do these by hand. All right, let's distribute 2/5 through. So if you gotta write it on the side, kind of look at it, 2/5 times 4. Just made 4 over 1. So you really have 8/5 there. I'm just going to leave it 8/5. 2/5 times 5 halves. What's 2/5 times 5 halves? 1. Now, can we simplify 8/5 minus 1? Because 1 is what in common denominator style for this problem? 5/5. So some of you probably already done, got the answer. 8 minus 5, 3. So I don't know how much fractions you probably came across in honors geometry, just always good to review and practice our fraction operations. Okay, I've taught you really nothing new so far today. Only thing maybe, kinda, I might have new for you is coming at you. So we're going to use set notation, interval notation throughout this class. When we do domains and ranges, sometimes they ask you to give it an interval notation. So we're just going to kind of start and practice that before we get into the domain and all that sort of stuff. So first let's talk about a set. So a set is a collection. This is a sloppy T of objects and these objects are called elements. So wordy. So a set is just a collection of different things. Could be a collection of numbers, could be a collection of variables, could be a collection of anything. That's all it is, okay? So some different notation here. So this here, A belongs to S. That's what this little kind of looks like a E symbol. A belongs to S, means A is an element of S. And then of course when you have the little slash through it, that means of course common sense it's not an element. It doesn't belong in there. So couple ways you can list these sets. This is probably, this one, I probably tend to use that the most. You can use braces to list it. Braces are the curly, kind of the curly parentheses. 1, 2, 3, 4, 5, 6. Those are your elements in there. You can use, this might be new to you, this set builder notation. We're going to kind of use both here. Now, the set builder notation is kind of referring to this piece here. You're like, what the heck is that? So how you read this? X, that vertical bar, such that X is an integer, X is between 0 and 7. So that vertical bar kind of means the phrase such that, X such that, blah, 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 whatever they're going to tell you. So, and we're going to kind of mix and match and use both of these. Okay, union. So much vocabulary today. Or, it's kind of what I remember. Union, the elements in S or T. It could be in either set. And then the other big one we're going to use a lot in this class, intersection. And it has to be in both of them. So you're looking kind of for the overlap. And just to point out to you, these are mathematical symbols. So this, I know it looks like a capital U. It technically means the union. That's the mathematical symbol for union. This guy is the mathematical symbol for intersection. So you also just little notation here to memorize or to keep straight in your head. Union, and that's easy, it looks like a U, union, but that's your or, intersection is the and. And of course you could have where there's nothing maybe in common, or the power did just flicker, that wasn't my imagination, that's okay. You could have the slash through there, which means of course it's empty, there's nothing in common in the sets. So kind of some crazy notation, but we're going to practice it. All right, so you've got your sets there, different numbers, you got your 3 different sets, find the sets, S, union T, intersection, and our last one, intersection. So let's start with, let's do the S, that's an S, a sloppy S. Very sloppy yes there. Okay, remember, union or. So I'm looking for numbers in S or T. S or T. What do you got for numbers in S or T? 1, 2, 3, 4.
5, 6, 7.
You got it. So or, whatever's in either of them, doesn't matter. Now the next one's a little more important, because notice your symbol switches. So that's your intersection. So we're doing S. So remember, for intersection, it has to be in both. So what is in both S and, oh sorry, we're doing V first, aren't we? Yeah, let's just switch it. Sorry, might do them in order here. What's in both S and V? Nothing. Okay, so how again, symbols, the null set, the empty set. It looks like a no solution symbol. It's kind of the same style when you write it. All right, let's do now S. I was getting ahead of myself here. S intersect T. So what is in both S and T? Not lot. What's in both? 4 and 5. Yep. So again, simple. You just have to keep those symbols straight in your head. Union, the U or could be in either, and has to be in both. And of course, you could have nothing and you got the empty set. Okay, so some more crazy interval notation. Now, and we're going to practice this here on the next page. We're going to write some of these out. All these crazy, lovely inequality symbols. I'm not going to get crazy and go through every single one of this. You'll figure it out. So basically the difference is you've got these parentheses in here. You have brackets in here. So when you think about your inequalities, parentheses, they're tiny. Notice they're open circles. And then the bracket has that filled in closed dot circle on it. So parentheses mean what we refer to as open intervals. So the endpoints are not included. I needed a bigger blank. Not included. So if you had an open circle on 3, that means you can get super close to 3, 2.99999999999, but you're not actually going to use 3. You would use up to 3. If you have a bracket on it, that is what we call a closed interval. And the endpoints are included. So where you have the closed, if I had a bracket on 3, I'd have a solid filled in dot on it, so the number 3 now actually is part of our answer set. So little symbols, but they mean a big thing. Parenthesis open, so up to that number, but not actually the number. Bracket closed, you can actually use that value. So we're going to practice that. Flip the page. Express each interval in terms of inequalities and graph it. Now, I think it's easier. I'm going to kind of flip-flop. I know the directions are what the order I wrote them, obviously. But I think it's easier to flip-flop it, meaning I'm going to graph it first. I think it's easier to do the graph on the number line, and then I'm going to write out the inequality. So I'm just going to draw my little generic number line here. We're not going to get crazy and put like 10 different numbers in it. We're just going to put what we've got. So smallest answer. Now your intervals, of course, notice all of these are smallest to biggest. They should always be written in chronological order, smallest to biggest. So -1, 2. If you want to put all the dashes and the numbers in between them, be my guest, not required. Now, -1 bracket, closed dot on -1. It's included. 2, open, parenthesis, up to 2, so open circle. And this is telling you your answers are everything from -1 to 2. So I'm going to shade in the middle. So 0 is an answer, 1, 1.9782, 1.99999, but not actually 2 is an answer. Now, how we're going to write these inequality style. Just because it's new, let's practice our set builder notation for that. So I'm going to use my little curly brace. Hopefully you draw yours better than I do. X such that And I'm looking at our graph, of course. All our answers are in between -1 and 2. So I'm going to put -1. I'm going to leave a little space because I'm going to put an inequality symbol in a second. X, 2. So I'm just going to fill in the appropriate symbols. The second symbol is probably the easiest one. Clearly, we're on the left side of 2. We are less than 2. We are on the right side. Our shading's on the right of -1. So we are actually X is greater than. I'm going to put the equal to symbol on because, of course, we have the closed dot circle. So there, oh, let's close it up. So there's your set builder notation. Now, I don't care if you do the inequality first and the graph second, whatever, but just be able to do both. So let's try this guy. So 1.5 up to 4. We got it, piece of cake. 1.5, 4. Open circles, closed circles, or a mix. What do we got? Closed circles. Our answers are in between there. So I'm going to shade that. I'm going to write out my fancy set builder notation. That might be the best brace I've drawn today. So 1.5. Now closed circle, so I'm going to do less than or equal to. And remember, you're like, wow, less than or equal to, you're on the right side. You always read your inequality from X. This is really X is greater than or equal to 1.5 when you read it from X. Ooh, infinity. Okay, all right, I got it. So our answers are -3 to infinity. All right, let's number line it here. Now, I can't actually put like infinity on the number line, so I'm just going to throw -3 on. If you want some other numbers, be my guest. First question. Open or closed circle on -3? Open, we have parentheses. So our answers, our solutions, our values from -3 all the way out to infinity. So it's the entire right side of -3. That is a truckload of answers in there. So when we write this one in our set builder notation, we only have one inequality. We are greater than -3. And that is it, my friends. Parker, did you have a question?
No.
Okay. And notice on infinity, there's a parenthesis on it. Infinity always has a parenthesis on it because you can't actually land on and include infinity. It's kind of one of those vague numbers that goes on forever. So infinity always will have parentheses. It'll always be the open circle. So this is probably the only new stuff I have for you today, okay, is all of this crazy notation. Any questions on any of this? All right, it's easy, just new. Same thing, still easy, just all this crazy set notation. So finding unions and intersections of intervals. So it says graph each set. All right, let's start with that. Now, it's up to you how crazy you want to get or with your graph here and draw this and whatnot. Of course, the first one I'm going to get like super carried away right here, and I'm going to draw each of them. So I'm looking at my numbers, kind of regretting the 7. It's kind of big. So I got to go from 1, and we got 7. So I'm just going to 1 through 7 on it for right now. 3, 4, 5. So I'm just kind of looking at the numbers in each set there, what I've got. So this first one, I'm going to do that one in red. I'm just going to color code it quick. So just like the last one, I'm just going to pretend there's only that one interval on there, and I'm just going to mark it out right now. So from 1 to 3, open circles in between. Tab. I'm going to do 2 to 7 in green. Make it look like Christmas here. Okay. So now 2 is going to have a closed circle to 7. Closed circle. So many different colors there. Now, final answer. We're after the final answer. So we've got to, of course, look super close at our symbol. So that, of course, is our intersection symbol. What is in both? So I'm looking, it's like Christmas here, where the green and the red overlap. So I'm looking for kind of right there where they're overlapping, my green and red colors. So I'm like, ooh, okay, they start to overlap here at 2, and notice green 2 has a closed circle. So I'm going to say my final answer is 2, and it ends where the overlap? 3. That's the only teeny tiny little spot they overlap. Now, closed or open on the 3? Open, so I'm going to use a parenthesis. All right, let's do the next one. So notice kind of the same number, so I'm really just going to draw the same number line, 1 to 7. Got the same number line. Same thing, I'm going to go Christmas style. I don't know, I'm in a Christmas mood, I guess. I'm going to do 1 and 3 in red. So open circles, it's the same thing. 1, 3. I'm going to do the 2 to 7 in green again. Close circles on both of those now. 2, 7. And then we're going to underline this in green, figure out our final answer off our symbol. So this time we have union. Union means or. So I am just looking for all the answers on the number line. It does not have to be the overlap. Well, what's our smallest number on the number line we have? So we're starting at 1, and we end at 7. Got it. So any questions on our unions, intersections? This absolute value stuff, probably you already could do the problems without all this crazy explanation. Okay, absolute value. If you read this to me, this looks about as clear as mud. There's like so many little criteria on it that I think it gets it way carried away. Absolute value, short and sweet. The distance a number is from 0 on the number line. Doesn't matter if you go right or left to 0. I'm just looking at the overall amount of units. You would go right or left from 0 on the number line. So I know you know it. What's the absolute value of 8?
8.
What's the absolute value of negative 8?
8.
Okay, let's just do these next problems and be done. D might be a little trickster. I gotta have something good for you. All right, you know these. Absolute value of 3. Absolute value negative 3. Absolute value of 0. 0. Three minus pi. Now, okay, let me give you some hints here. 1, I want an exact answer. Now, when I say exact answer, that means we're not going to round off some crazy-decimal. I want my answer to have pi in it. So the first thing I would ask is try to maybe mentally figure out 3 minus pi. What's 3 minus 3.14? Negative 0.14. So I'm kind of, this is my thought process. This is my answer. What's the absolute value of that? 0.14, right? So I need some exact crazy expression that has pi in it that's going to yield me 0.14. Jack, right?
Couldn't you just do pi minus 3?
Got it. Why am I writing an M? We said, I'm losing it. We said it. I should write it. Okay. Pi. So that would be your exact answer versus just putting 0.14. We want an exact style. That's the only trickster of the day. That's all I got for you. The next thing, of course, I mean, you can figure this out. Again, a little carried away, a little dramatic here. I'm pretty sure you don't even need the top blue box on the slide here. Distance between the points. If A and B are real numbers, the distance between the points on the number line, you can subtract them and do the absolute value. That seems like a whole lot of extra work to me. I'm just picture the number line. To go from negative 8 up to 2, you cover how many units? 10. Why are we making this any more complicated? I mean, if you want to get technical about it, but as long as you got the 10, I'm going to be happy with you. Any questions on that? So a lot of the problems today you'll see on the homework do not require very much work.